Today we are working on some systems review. So our content objective is students will be able to solve a system of two equations by either graphing using substitution or the elimination method. Our language objective is students will be able to discuss ways of checking if the solution you derived is truly a solution. And why am I learning this? Well, of course, it's important for real world problems. So first thing I want to go over is graphing. So there are three different outcomes. The first one is if the lines intersect once. In that case, there is one solution. Number two, if the lines are parallel, which means they never intersect, the answer would be no solution. So notice here, what you're going to notice is the slopes are going to be exactly the same. However, the y-intercepts are different. So the rate of change is the same, but they start at different points. And number three, if the lines are right on top of each other, so in other words, if the lines coincide, they touch infinitely many times, so the answer is infinitely many solutions. And what you're going to notice about this type of problem is you're going to notice that the equations are both equivalent to each other. Okay, so for number one, what I'm going to do is go ahead and give you the steps of how you would do this, kind of a quick reminder, and then for the second one, I would go ahead and have you pause the video and try it by yourself. So here, with your matching homework, you're going to notice, I believe it's number 13, 14, I could be totally wrong, or number 7 or 8. It's going to ask you to turn standard or any kind of form into slope-intercept form. So that's what I'm going to show you here, just to kind of give you a refresher. When you're graphing, it's really nice if your equation is in slope-intercept form. It makes it a lot easier. So in this case, quick reminder, slope-intercept form is essentially y equals mx plus b. So in other words, you're trying to isolate y. So that's exactly what I'm going to do with this equation here. I'm going to do x plus y equals -1. To solve for y, I need to first eliminate the x on the left. So I'm going to subtract x from both sides. This is going to go away, leaving me with y equals -x minus 1. And there you have it. Our equation is now in slope-intercept form. I can see that my y-intercept is going to touch at -1, so I'm going to go ahead and write that right now. It's going to touch the y-intercept at -1. My slope, okay, there's no number in front of this x. However, I do know if there is no number, there's automatically 1. So our slope is -1. For slopes, it is preferred that it's written as a fraction, so I'm going to go ahead and turn this into a fraction. That way I can see that the rise is -1 and the run is 1, so it's going to go down 1 to the right 1, down 1 to the right 1, etc. until I have no more space. I could even practice going the opposite direction, so up 1 to the left 1, and you know I prefer for you to have as many points as you possibly can until you have no room left. This helps ensure that your line is as straight as can be. And then let's go ahead and transform our second equation, because unfortunately it's not in slope-intercept form either. So 2y minus x equals 4. So trying to isolate this y, it would actually be easier to eliminate this -x first. So I'm going to add x to both sides, leaving me with 2y equals x plus 4. Last but not least, I need to isolate my y. This means 2 times y, so the inverse would be to divide both sides by 2, and in this case, each term by 2, which leaves me with y equals. Now here, yes, you can write it as x over 2, but to reveal the fraction, if you put a 1 in front of this x, because there's one of them, it would be better for you to write it as 1/2 x plus 2. So here, I can see that the y-intercept is at 2. Let's plot that point. And my slope is 1/2. So it's basically a rise of 1 and a run of 2. You continue this until you can't go any further. And then, of course, practice going the opposite direction. And, of course, you can then draw your line. So at this stage, of course, you know what I'm going to say. I'm going to say that I think the solution is -2, 1, and the reason why I would say I think is because, of course, we need to check our answers. So let's do that real quick. If our solution was -2, 1, where the x's are -2s and the y's are 1, let's check to see if this really does work. So for x, I'm going to put negative 2 plus y, which is 1, is supposed to equal negative 1. Is this true? Well, negative 2 plus 1 is indeed negative 1. So it works for the first equation. Well, let's check the second equation. So here we have 2 times y, which is 1, minus x, which is negative 2, is supposed to equal 4. So here we have 2. A negative times a negative is a positive, so 2 plus 2 equals 4. Is this true? Yes. So I can confidently say that the solution to this system is indeed negative 2 comma 1. Now, one thing to consider is what this solution represents is this is the only solution that will leave true statements in both equations. So this is the only one, okay? So now what I would like you to do is go ahead and pause the video and try number 2 on your own. Okay, so let's see how well we did. So for the very first one, I hope you recognize it's already in slope-intercept form. So you can go ahead and identify, hey, my y-intercept is 1, my slope is negative 1/2. And just go ahead and graph it here. Y-intercept is 1. Use your slope of negative 1/2, so down 1 to the right 2, and draw your line. Of course, the more points, the better. So here, you would have drawn more points before you graphed. For the second equation, unfortunately, it's not in slope-intercept form. Just a quick reminder, it's y equals mx plus b. Definitely not in that form. So first, we're going to get rid of x. And then from this point, we still need to isolate y. So we're going to go ahead and get rid of the 2 by dividing each term by 2, each side by 2, sorry, leaving you with y equals negative 1/2 x plus 3. So here I can see that my y-intercept is 3, and my slope, so I'm sorry, go ahead and put that point down, and then use the slope of negative 1/2 to get further points. So down 1 to the right 2, and down 1 to the right 2, and just go in the opposite direction as well. So here, for some strange reason, a lot of my students have been claiming that this graph tells me it's infinitely many solutions. This is incorrect. I repeat, this is incorrect. Because if you ask yourself, how many times do these lines touch? How many times do they intersect? Your answer is hopefully is never, none, zilch. They never touch. In fact, you could extend these lines as long as you want and they will never touch. So the correct answer is actually no solution. Okay, so please don't accidentally write the other answer. So here, basically what this means is there's absolutely no order pair that will make a true statement for both equations. Okay. What you're going to notice here is your slopes are identical in both equations. However, they have different y-intercepts, which means they start at different points. Okay, so now let's go ahead and practice substitution. The one thing about substitution is you want to at least have one equation where the variable is already solved for. So in this case, I know the value of y, it's in the form of 2x. So essentially I can use that 2x, substitute it in for my y, and go ahead and solve from there. So again, the key thing about substitution is you want to make sure at least one variable is solved for. So let's jump into our example here. For this one, you're going to see that unfortunately none of the variables are solved for, which is okay. So what do? Whoops, I got ahead of myself. What we're going to do is go ahead and isolate one of the variables. You can choose to isolate the x's or the y's from the first or the second equation. I am personally going to isolate the x in the second equation. Why, you might ask? Well, because the coefficient is a -1, that's going to make it impossible to turn a whole number into a fraction. I'm going to want to stick with fractions, okay? And why is it impossible? Well, because if you think about it, dividing a whole number by 1 will never change it into a fraction. And dividing a whole number by a -1 will never turn that number into a fraction either. So it's impossible. Now, if I use any other coefficient other than 1, like maybe 2, there is a chance that I might create a fraction. And for me, I'd rather work with whole numbers. So Let's go ahead and do that. Let's isolate x in the second equation. So first I'm just going to write it, negative x plus 2y equals negative 14. Here, if I want to isolate my x, I'm going to have to get rid of this plus 2y by subtracting 2y from both sides. I have now negative x equals negative 2y minus 14. Last but not least, I'm going to have to get rid of this negative. So if you want to, putting a negative 1 up front might help you remember and understand it is negative 1 times x. So the inverse would be to divide everything by negative 1. The negatives cancels out, and so does the 1, so I'm left with x equals. Here the negatives cancel out, leaving me with 2y. The negatives cancel out, leaving me with plus 14. Now I know the expression for x, so I'm going to go ahead and use the other equation, which is the first one. Negative 5x minus 4y equals negative 28. What I'm going to do now is take this expression 2y plus 14 and substitute it in for x. Why x? Because here it says x equals. So now I have negative 5 times 2y plus 14 minus 4y equals negative 28. Here you're going to have to distribute, so negative 10y minus 70 minus 4y equals negative 28. At this stage, I can go ahead and combine like terms, so negative 14y minus 70 equals negative 28. Here, just add 70 to both sides, leaving me with negative 14y equals, let's see, 42. Divide both sides by negative 14. I'm left with y equals 3. Remember that we're not done quite yet. We're going to have to take this value and substitute it into one of the original equations. I'm going to go with the second one because it seems a little bit more simple. So negative x plus 2y equals negative 14. I'm going to go ahead and take this value and substitute it in for y. So we have negative x plus 2 times 3 equals negative 14. We have negative x plus 6 equals negative 14. We're going to go ahead, whoops, made a boo-boo. Right here, 42 divided by negative 14 is a negative 3. Let's fix that. So this should be negative, and this should also be negative. Okay. In fact, this was actually a very common mistake in the classroom, and even I made it, so please be very careful. In fact, if you would have checked your work, it wouldn't have worked out, and that would have been a red flag for you to check your work. So here we're going to add 6 to both sides, leaving me with negative x equals negative 8. Divide both sides by negative 1, and I'm left with x equals 8. So here I'm going to say that I think the solution is 8 comma negative 3. And of course, I always say think because we still need to check our answer. So let's do that. If we had 8 comma negative 3, where x's are 8s and y's are negative 3s, let's see what we have. We have negative 5 instead of x. I'm going to write 8. Minus 4y instead of y, I'm going to put negative 3. Equals negative 28. So here we have negative 40 plus 12 equals negative 28. Here we end up with negative 28 equals negative 28, so it works out for the first equation. Now let's try the second one. So we have negative instead of x, we're going to write 8, plus 2 instead of y, I'm going to put negative 3, equals negative 14. So here we have negative 8 minus 6 equals negative 14. Is this true? Yes. Because it works for both, I can confidently say that the solution to this system is indeed 8 comma negative 3. In fact, this is the only solution that would yield true statements for both of these equations. Okay, so at this stage, I'm going to go ahead and have you pause the video and try number 4 on your own. Okay, so let's see how well we did. So for this one here, if we're using substitution because we're following instructions, what would I do? Well, first I would write the first equation because it's already solved for y equals 2x plus 3. So I'm going to go ahead and take this value and substitute it into the other equation, which just so happens to be y equals negative 2x minus 9. So here, we're going to go ahead and take this value and substitute it in for y. So here we have 2x plus 3 equals negative 2x minus 9. At this stage, a lot of students are going to want to move the constants over. It's not wrong. However, to get you in the habit of it, it's actually better for you to move the variables first, because then it's going to look like something that you're used to seeing. So by moving the variable over, I do prefer to move it to the left, my preference. We're going to be left with 4x plus 3 equals negative 9. So now it looks familiar. So I'm just going to get rid of my constant, and I'm going to be left with 4x equals negative 12. Simply divide both sides by 4. Now I'm going to get x equals negative 3. Now a common mistake was a lot of students made this a positive 3 instead of negative. So be very careful. Recognize that here there's no negatives that are getting canceled, so it's going to remain negative. Now that I know what x is, I'm going to go ahead and plug it back into one of the originals. So now we have y equals 2 times negative 3 plus 3. Here we have y equals negative 6 plus 6. So y equals negative 3. So at this stage, I can say that I think the solution is negative 3 comma negative 3. Of course, we always say I think because we have to, of course, check our answers. I'm going to believe that you went ahead and checked your answers, and it should work for both equations. So now moving on, let's go ahead and try number 5. Okay, before we move on to number 5, we should first talk about the next method, which is elimination. With elimination, there's going to be various ways of eliminating a certain variable. So your methods might vary from your partner's, and that's totally fine. So here, I am going to highly suggest that you eliminate the variable that requires the least amount of work. So in this case, if I were to look at the x's and the y's, I would definitely see that eliminating the y's is going to be easier because it would only require me to change one of the equations. So a lot of you are thinking, yeah, just multiply the second equation by 3. Correct. But now before we move on, let's take a close look at something. Both of these are negative. Now that's not going to help us in eliminating, because in order for something to eliminate, we need a positive and a negative. So when the signs do match, you should look forward to multiplying an equation by a negative number. So here, if I want to eliminate the y's, I'm going to have to change the second equation by a negative 3. So here the first equation is going to stay exactly the same. But the second one, once you multiply each term by a negative 3, this is what you're going to end up with. And what's nice is you can recognize that the y's do eliminate each other, so you know you did something right. If they don't eliminate, that means you should look back into your steps and see what you did. On that note, let's go ahead and try number 5 together. So here, I'll be completely honest. It really doesn't matter if you eliminate the x's or the y's. Some depends on the person. They can be ranked as equally the same by difficulty. So here, if I wanted to eliminate the x's, I would have to change this second equation by multiplying it by 3. Okay. Now, if you wanted to eliminate the y's, you would also change the second equation. But here, since they're both positives, I would actually have to multiply by a negative 4. Now, is it right or wrong to choose one over the other? Absolutely not. But for me personally, I do prefer the smaller numbers, and not only that, if I can, I'll always choose to multiply by a positive number. So I'm actually going to go with my first option, which was to multiply by a positive 3. So this first equation is going to remain the same, so 6x plus 4y equals 22. As for the second equation, it is going to change. I'm going to be left with negative 6x plus 3y equals 6. Here the x's are going to cancel out, leaving me with 12y I multiplied instead of added. Let's try that again. 4y plus 3y is 7y equals 22 plus 6, which is 28. Divide both sides by 7, and I'm left with y equals 4. Now that I know part of it, I just need to plug it into one of the originals. I'm going to go ahead and choose the second equation, negative 2x plus y equals 2. I'm going to go ahead and plug in my 4 in for y, which leaves me with negative 2x plus 4 equals 2. Now we're going to get rid of the constant first, so negative 2x equals negative 2. Divide both sides by negative 2, and I'm left with x equals 1. At this point, I can go ahead and say that I think the solution is 1 comma 4. And the reason why I say think first is because I still need to, of course, check my work. So let's go ahead and move on to that. So if I'm claiming the answer is 1 comma 4, I'm going to plug in 1 for x's and 4 for y's. So here, 6 times 1 plus 4 times 4, does this equal 22? Let's see, 6 plus 16, does it equal 22? Yes, so it does work for the first equation. Now I say this a lot. Is it good enough just to check 1? The answer is no, because by definition, in order for it to be a solution to a system, it must result in true statements for both equations. So let's try the second one. We have a negative 2x plus y. Oops, let's go ahead and start plugging in. Negative 2 instead of x, let's plug in a 1. Plus y, let's plug in a 4 equals 2. So here, negative 2 plus 4 equals 2. Negative 2 plus 4 is 2. So guess what? It does work for both, so I can confidently say that the solution is indeed 1 comma 4 for this system here. Okay, so now let's go ahead and pause the video and try number 6 all on your own. Okay, so let's check out number 6. Here, hopefully you recognize that it would be easier to eliminate the x's, but before we even go into that, I want you to recognize in order for us to start elimination, both equations need to be in standard form, which is ax plus by equals c. Okay, in other words, x's and y are on one side, the constants on the other, and you want to make sure they're lined up. Here, you're going to decide it's easier to eliminate the x's or the y's. I'm going to say x's for sure, because I see that 4 and 6 have a 12 in common. 6 and 5 have a 30 in common, so I would have to multiply by larger numbers, which I don't ever want to do. If I want to, I always want to keep things more simple by multiplying by a small number. So here, I'm going to have to change this first equation by 2. And that's going to change my equation to that, and change the second equation by a negative 3, which would change my equation to that. Now, could there be differences? Absolutely. Some of you may have made the 2 negative and the 3 positive. That's also an option, okay? And again, if you wanted to multiply by 4 up here and 6, negative 6, that would work as well, but try and always keep your numbers as small as possible. Here my x's would cancel out, leaving me with negative 3y equals 9. Now a very, very common mistake that I noticed was when my students chose to make this 2 a negative and this 3 a positive, they made some calculation errors when combining the constants together. So please just be very careful. So here, divide both sides by negative 3, I'm left with y equals negative 3. Now that I have that, I'm going to plug it into one of my originals. I'm going to go ahead and plug it into the first one. I'm going to put negative 3 in for y, leaving me with this. So I have 6x minus 18 equals negative 6. Add 18 to both sides. I'm left with 6x equals 12. Now simply divide both sides by 6, and x equals 2. So my answer, I would say, I think, is 2 comma negative 3. Of course, I say think because I still need to check my work. I'm hoping that you went ahead and checked the work and it does work out. If you didn't get the answer and you didn't check it, please make sure you follow the notes on this slide here. Other than that, it's actually going to conclude the lesson for today. Thank you so much for tuning in as always, and until next time, bye.